Okay. So, good evening, everyone. Glad to meet you again this week. My voice is audible to everyone, right?
Yes, sir.
Okay, good, good. Okay, just a minute. I'll share my screen now. Um, Actually, the notes that I'm preparing for you guys is still not yet ready. Once I have prepared it, I will share the drive link on the chat box. Whoever wants can access it and can use, because I don't think we'll be able to cover everything in these sessions, because I also requested the professor, but I didn't get a reply yet. So I'll try asking again, and I'll let you know. In case we are unable to have a session, we will. I'll send you the notes. You can refer to that regarding the topics which we couldn't cover, especially solving more gate problems. So I'll just share my screen. So I hope my screen is visible to all.
Yes, sir.
Okay, okay. So today actually I thought of starting phase diagrams and alloy constitutions, but we can't go there without completing Miller indices and crystal imperfections. So we have to rush this time. We'll go. I'll go. I'll try to go as fast as possible. Okay. So we'll just briefly look at the summary of previous class. Today I do not know how much I can make it of an interactive session, because in 1 hour I want to somehow finish up to defects, so it will take quite a while. We'll do our best to have an interactive session, but hopefully I mean, I think it may become a little hard, so hopefully we may have some interactions here and there. So in the previous class, we saw about the different metallic crystal structures. So how they are packed. Say for example, simple cubic structure, body-centered cubic structure, face-centered, and then we also saw the stacking sequences. One person did ask about why the face-centered cubic structure is stacked in that ABC pattern. I still haven't got a proper justification for that. So don't worry, I'll continue to look into it. I'll somehow get the answer to that particular question. I haven't forgotten it yet. In HCP also we were kind of looking into it, but since time was over, we had to move on. So today we will start with HCP structure, and then we will continue with the others. Then we will we'll also see perovskite structure. I thought we could see it last class, but we couldn't. We'll just see what the perovskite structure is. We won't go much into the details. This is just for 1 marks, which could possibly, sorry, yeah, potential 1 marks in the gate. So we will see perovskite structure, and then also we'll see about linear and planar density, how to calculate the linear and planar densities of a crystal. So the chances of you getting that as a question is high. Then we will see crystallographic directions and the family of directions along with the Miller indices. Then we will also see the crystal imperfections such as point defects, line and surface defects. So as usual, what we saw last time, we saw the HCP structure, right? So we know that the stacking sequence is AB sort of a stacking sequence. Um, then we also know that the coordination number is 12. Yeah, and then we have atomic packing factor as 74. So that we will look at right now, how we calculated the APF, and how we did the C by A ratio. We will look at right now. Okay. So sorry. In here it is actually 6 atoms per unit cell. We will also discuss how that is 6 atoms per unit cell, and uh, some of the examples here is cadmium, magnesium, titanium, zinc, calcium. Calcium also comes under HCP structure, and many more. So we will see them. So we saw, right, in last class about the lattice parameter, how to find the lattice parameter. So lattice parameter is A, right? Oh, sorry, it went too far. Okay, lattice parameter is A, right? So how do we usually find it? Um, any idea for HCP? Okay. See, lattice parameter is pretty simple. For HCP again, we let us take some, some edge plane, like sorry, so some base plane, either the top plane or the bottom plane. Okay, it will be somewhat like this. It will be larger actually. This is like a hexagon. Na? Here we want A. So A is nothing but the interatomic distance, also known as the lattice parameter, and that is usually assumed to be the center of one atom to the center of the other atom. In our case, it is R and R. So A is equal to R plus R2 radius, 2R. So we can also say R is equal to lattice parameter by 2. So this is, let's see, A lattice parameter. So we saw this. Next, number of atoms per unit cell, right? So it is, we know it is 6, but how did we know it is 6? So there are 6 atoms. Just a minute, just a minute. Sorry. Thought I got some notification. Okay, yeah. So yeah, to find the number of atoms per unit cell, it is the let's first take the number of atoms at the um, uh, one plane, say top plane. Okay, how many atoms do we have in the top plane? So we have an arrangement like this, right? One, then central atoms, then the other. So this is the top plane, this is the bottom plane. So in the top plane we'll be having 6. So 6 atoms in the top plane divided by 6. Each one is shared by 6 other unit cells. So we have 6 into 1 by 6. Then we have the bottom arrangement, right? 6 into 1 by 6. Top plane, the same here in the bottom. Okay. Then we have um, one atom in the middle, right, of the top and bottom planes. So these two atoms are in turn shared by 2 unit cell. So 2 into 1 by 2 plus we have 3 exclusive atoms in the middle which belong to this particular unit cell alone. Okay. On the whole, what do we have in total? We have, this becomes 1, this gets cancelled, so 1, 1, 1. So 1 plus 1 plus 1 plus 3, a total of 6 atoms in the unit cell, right? Now we got it. So now let us calculate the C by A ratio. Okay. To find the C by A ratio, what we should do is, as I mentioned like last time, we take just half of the unit cell. Okay. And then I'll draw the hexagon here. Let's assume this to be the bottom. Okay. So let's say 6, and 1 in the middle, and then 3 on top. Okay. So first what we do is we draw a triangle here. Okay. We know, right, this hexagon, sorry, this hexagon can be classified into different triangles, right? 6 triangles, 1, 2, 3, 4, 5 and 6. So of this we'll just take one triangle, and in that triangle let's have a perpendicular bisector over here and over here. Okay. The meeting point of the bisector, two bisectors here, sorry, this from this place and this place. Okay, the meeting point is usually in line with the atom, um, with one of the atoms which is suspended in the middle of the unit cell. Okay, so the height, the total height is c by 2. Okay. um, I also explained in last class why this is c by 2 and not c, right? Then we will connect this edge, sorry, to this particular atom. Okay, just a minute. Okay, now we will name the points. So this is point A, this is point B, let's call this point O, this is point C, and then let us call this place point Y, this bisector end as point Y, somewhere around here, and this is point, sorry, this is point X, the middle of the two bisectors, right? Now let's take triangle A B, sorry, A Y and B. Okay, which is nothing but this triangle. Okay, sorry, AYB is this one, sorry. Okay, let's draw it here so that it will be in detail. Yo, what's happening? So this is A, this is B, and this is Y. Okay, we know that the angle between this is 30 degrees. Why is it 30 degrees? Because we are taking, let's say this is AOB, right? And this is a equilateral triangle. A hexagon can be divided into 6 equilateral triangles. Okay, equilateral triangles. And equilateral triangle means you have total angle is 180 degrees, right? 180 means 60, 60, 60, of which we are taking half. Bisector, right? Bisector means half. So half of 60 is 30 degrees. That's why we have a 30 degree over here. Just a sec, above the rest. So now we will see what data we have. We already know the value, I mean A and B. So A to B is nothing but the side A. Okay, side means like we can call lattice parameter or interatomic distance, that is A. Okay, we already know that. So this is A. Okay, then when it comes to BY, right, this place, BY we do not know, right? So by is we can say just we can keep it as by. Then ay, ay also, do we know? It is the hypotenuse, so we don't know yet. But using trigonometry we can find the value of AY. So how is it? We know the angle and we know one side. So let us assume this to be the adjacent side and this to be the hypotenuse side. So what can we do now? Does anybody know? Can anyone tell me? Am I audible? Hello? Uh,
Please repeat the question again, sir.
okay. The question is just a minute. There's something wrong with my connection. Yeah. Um, the question is in this triangle that you see over here, right? We know this data, the angle and the one of the sides. So how can we find AY, the value of AY?
Sir, by applying trigonometric ratios,
Yeah,
cos theta.
exactly, cos theta. So we put cos 30 degrees equal to adjacent AB. Uh, sorry.
By AY.
Yeah, no. Here we made a mistake last time. It's actually AY by AB actually, not AB by AY, because if we put it in that way, like I was unable to solve the problem correctly. So it's actually AY by AB. This AB is the hypotenuse. Okay. So we know this. Okay. Sorry. Where is? Yeah. Okay. So we know AY we don't know. AB is nothing but your A, and so to find AY it is A cos theta, and cos 30 degree is root 3 by 2, right?
Yes, sir.
So A into root 3 by 2. Now we got the AY value. Okay. Now we have to find AX value. Okay. We know that AX is 2/3
Of
of
AY.
AY, right? So 2 by 3 of A root 3 by 2. So so these two get cancelled. Then you have A root 3 by 3. Wait. Sorry. What am I doing? These two also get cancelled, and we have a root 3 over here. So finally we get AX is equal to A by root 3, right? Now we shall go for the triangle AXC, right? Where is triangle AXC? A, X and C, the one on top. Okay. In triangle AXC, we use the okay. Let's draw it. Okay, we have A, we have X, and we have C, right? Sorry, it's right angle triangle, not equilateral. It's right angle triangle. Sorry. Okay, this is C by 2, is it not? And we already know AX, that is A by root 3. We can use the usual Pythagoras theorem to solve and find out AC. Okay. So AC square is equal to AX square plus XC square. AX square is A by root 3 whole square plus X is C by 2 whole square, right? So if we simplify this, and also we have to take AC over here, right? Its value to be A. So if we put AC's value here as A, okay, we take it as A, we get A by 3 plus C by 4, right? So we have A, and then common denominator 12, we have 4A plus 3C, right, which is equal to 12. We take the 12 here, 12A minus 4A is equal to 3C. Then that's 8a is equal to 3c, and c by a is equal to 8 by 3, which is approximately equal to 1.633. Okay, so
Sir,
yeah.
for each A and C, there must be a square above on that term.
Uh, oh, okay,
A
okay.
square and C square, respectively.
Sorry. Yeah, I forgot about them. So sorry. Yeah, here you have squares. So you'll have a square here, you have a square here, and c square also. Square, 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 and yeah, you have to take square root if you want to find the c by a ratio. So square root of 8 divided by square root of 3. Again, if you see, it will be 1.633. So thanks for letting me know that. Um, this is your C by A ratio, and this could be a possible question, right? Oh, just a minute. Okay. Um, yeah, right. Coming back. Next, we have to find the atomic packing factor, right? So to find the atomic packing factor, we'll be having, the usual formula, right? APF is equal to volume of volume occupied by by atoms to the volume of unit cell. I guess this itself would take most of the class. So okay. So volume of the atoms occupied by the unit cell is nothing but, um, we have pi a cubed, right? Wait. Sorry. Volume of atoms. So let's keep this as small v, and let's keep this as capital V, right? So volume of atoms volume occupied by the atoms is nothing but, we know that there are 6 atoms in the unit cell, and each atom's volume is sphere. It's sphere, right? Solid sphere. So 4 by 3 pi r cubed, and if we solve this, right, it will be 4 by 3 pi. And if we remember in the last class, I mean, no, not in last class, we solved, right, r is equal to a by 2 cubed, and then we finally solve it, the volume will be like pi a cubed, right? So we get pi a cubed over here, and then for the volume of the unit cell, so it is nothing but 6 into the area of the triangle AOB, okay, and times the height. So what is the triangle, the full triangle AOB? We just saw, right? Let's take this as A, let's take this as O, let's take this as B, okay. So the area, what is the area? Area is half breadth into height, okay. So let's draw the bisectors. Bisector 1, bisector 2. Okay, this is point X, and in our case, half breadth we take as BO. Okay, and height we take as AY. So Y, I guess, comes over here, right? So we know the value of BO again is A, and the value of AY is Anyone remember? So it is root 3 by
Root 3 by
2a. Yeah, excellent, excellent. It's root 3 by 2a. So now we found the area of the triangle AOB, which is root 3a square by 4.
4.
Okay. With this, we will now find the volume. Okay, so 6 into root 3, sorry, a square by 4 times the height c. So if you solve everything, your final answer will be something like this: 3 root 3 a square c by 2. All I did this and this. That's all I did. So you get the answer here, and you substitute it over here: 3 root 3 a square c by 2. Finally, if you would solve all this, right, your answer will be 0.7404. I'm sorry I'm unable to solve all things steps because we are really running out of time. So this is kind of it. Okay, we have now seen the atomic packing factor. So this is kind of clear, right, for all of you guys? Uh,
Yes, sir.
yeah. Okay. So my screen is visible, right? No problem, no? Yeah. Okay, moving on. So now let's discuss this problem. Okay, since there is a lack of time, I don't want to ask you guys to solve it, but rather I'll just show the problem as to how to solve, and maybe in the coming classes I will give you like some practice problems. Okay, so let us take this particular problem. So we have a metal with HCP crystal structure, has lattice constants zero point 0.3 and 0.56 A and C. So we have to determine the volume of the unit cell. So this was a GATE 2013 question. Okay. So to solve this question, all we have to do is first we have to find this the volume of the unit cell, right? So we just have to find the volume of the unit cell, and volume is nothing but 6 into area of the triangle AOB times the height. We just now saw it, right? So um, we can put 6 into root 3 a square by 4 into c. C is nothing but here 0.56, and instead of a we put 0.3, direct substitution. Okay. Here I have again solved how to find the area of the triangle AOB. Okay, this part. So our final answer for this will be 0.131. Any doubts, guys, in this problem?
Sir, for that C by A that you solved in the previous problem, sir,
Yeah.
that was in all the case or it is some like मतलब किसी special case में ऐसा होता था?
No, no. C by A is constant for all case. Any HCP structure means C by A should be 1.666. Sorry, 1.633 something.
Okay, sir.
Yeah, it's constant only. Don't worry. Yeah. So actually, that is also a gate question. Like, what will be the C by A ratio? So okay, this problem is okay, right, for all? Okay. Now let's move to the next one. This is the perovskite crystal structure. Okay, so it looks like a combination of both BCC, right? So we have a body centered, and FCC. We have atoms at the face. So it is like a combination of both the um, body centered and face centered cubic cells. So the chemical formula for perovskite. So this can be a possible gate question. It is AbX3. So, and this was once asked, I guess again in 2013 or 14, I don't remember exactly, but this particular question was asked: the number of atoms that are present in the unit cell of a perovskite. So it is 5, because just like FCC, we have uh, 8 atoms shared by 8 unit cells, 4 atoms shared by four atoms at the faces. Four, wait, sorry, one, three, six atoms, right? Six atoms shared by uh, two unit cells each, and finally we have one atom at the center. So totally we have 1 plus 3, right? 2 3s are 6 plus 1, so we have 5. Okay, you guys got it, right? So the number of atoms per unit cell in perovskite is 5, and the formation and stability of perovskite is based on the Goldschmidt tolerance factor. So sometimes they may ask, like, what is it based on? Okay, how can we say a perovskite structure is stable? So the answer is the Goldschmidt tolerance factor, and the tolerance factor must be between 0.7 to 1. Okay, and so this is the formula for Goldschmidt tolerance factor. Radius of atom A, which is the corner atoms, okay, then radius of atom B, which is the center atom, and radius of the atom O, which are the face atoms. Okay, so you can note this formula, note the Goldschmidt tolerance factor, and also just a minute, someone's trying to enter. Yeah. Okay. So these are some of the examples of perovskite. If anyone wants, they can take a screenshot of this particular slide. So for different Goldschmidt tolerance factor, we discussed, right, from 0.71 to 1. For each Goldschmidt tolerance factor, you have one example of perovskite. So if it's 0.71 around that range, means it is like trigonal structure. Then if it is 0.71 to 0.9 means it is orthorhombic. Okay, and then it is 0.9 to 1 means it is cubic. Then 1 and above means it will be either hexagonal or tetragonal perovskite structure. So you can see the example. So they'll ask, like, they'll give one of these examples: barium titanate or strontium titanate or calcium titanate, and then they will ask which of this is orthorhombic perovskite or which of this is cubic perovskite. So you can take a screenshot of this particular slide and you can revise it afterwards. This could be one question. Then let's go to the theoretical density. So the theoretical density rho of any material is the mass of the atoms in the unit cell divided by the total volume. So what is the mass? Mass is nothing but the number of atoms per unit cell times the atomic weight divided by the volume of the unit cell and Avogadro's number, right? So let's see for each unit cell. This is BCC structure, right? And this again is another gate problem. Okay, if you see in this BCC structure, the atomic weight is 52 grams per mole. Usually this will be given, atomic weight and all they will give. So for atomic weight of chromium is 52 grams per mole. Interatomic radius is around 0.125 nanometers. We all know that number of atoms per unit cell is 2 in the case of BCC. So this we should be knowing. The question they will give only what structure it is. So we should remember that for BCC the number of atoms per unit cell is 2. Okay, and this also we should be remembering. So this lattice parameter is equal to root 3a is equal to 4r, right? What we solved from the previous time. So this also we should remember. Okay, then what we do is we just substitute the values. Okay, this is the number of atoms in the unit cell into its atomic weight, n into a, divided by volume of the unit cell, which is simple since it's cubic, it's a cubed, and then the Avogadro number. Avogadro number is a constant. Okay, so if you substitute means you will be getting your answer. It's around 7.18 grams per centimeter cube, or 7.19, around this range. So is this problem clear to everyone?
Sir, previous slides.
The previous slide, huh? This one? It,
Okay, sir.
yeah.
Sir, is this the only way of finding which atomic structure it is? मतलब material का कौन सा atomic structure है?
No, no, no. Actually, there are, for finding the atomic structure of the material, there are other ways. This is just the density.
Sir, by density also can we find this? The
Mm,
structure.
Density, to find the structure is a little difficult actually. So for finding out the proper atomic structure, right, you need to do something known as X-ray diffraction technique. So from the X-ray diffraction, you will be getting peaks. From the X-ray peaks, we'll have to find the like corresponding indices, Miller indices, and from that finally we can find out, okay, it is this particular material. I mean, not just that. That is one way. Another way is SEM EDAX analysis. That is energy dispersive spectroscopy. So these are some of the ways with which we can find what material it exactly is. Just a minute. Um,
Oh, so sir, मतलब I was telling that
uh-huh.
as like in simple cubic body structure, cubic FCC, these all has different number of atoms per unit cell.
Uh-huh.
One like one has one, two, four, six, eight.
Yeah.
So by this way, as density can be calculated by simple method only, like what is the volume of the material that we had taken and the mass by measuring the mass of it.
Mm.
So it can be found that way. And as we know, for example, आयरन है तो उसका जो मास होता है, मोलर मास, वो भी हमें पता होगा। तो
Ah.
उससे एटम्स पर यूनिट सेल वाले को हम Z मान लेते हैं, एक अ, मतलब जो हम फाइंड आउट करने वाले हैं, तो उससे फाइंड आउट कर सकते हैं क्या?
But purely we cannot say because um, like for different like sometimes the density could also be similar. You know, if these different parameters, though they are different, right? If for example the volume of the unit cell changes, right? Say for example, if it's in hexagon or something else, no, and then the atoms per unit cell also changes. There sometimes the value could be similar to each other, so there could be a clash. So we cannot entirely like find the material, like what material it is, just from the density alone. So usually the technique is, as I mentioned earlier, through X-ray diffraction. So that is how we usually find through X-ray diffraction and dispersive spectroscopy, energy dispersive spectroscopy.
ओके सर, ओके।
Yeah. Okay. Then we already know this, like what is a unit cell and all. So these are the 14 types of Bravais lattice. Okay. And you can, if you want, you can take a screenshot of this because it's important to know which metal has which structure. Say aluminum means FCC, copper FCC, alpha iron BCC. So the chances of they expecting you to remember these structures of well-known metals is high in gate. So better to take a screenshot or take a picture of this and remember this. Now we'll go to this problem. So the lattice parameter of beta phase titanium alloy is 0.2866 and atomic mass is also given. Avogadro number is again given. So we have to determine its density and atomic packing factor. So how will we find the density? And one more thing, here it is, sorry, beta titanium alloy. So in the previous slide we see that there is alpha titanium which is HCP, right? So please remember, alpha titanium means it is HCP structure, beta titanium means it is BCC structure, right? So please remember these two. Now, okay. We will come directly to the problem since time is running out. Okay. So this is a small science. Pure titanium can crystallize into either alpha or beta when it crystallizes to room temperature. So alpha is HCP structure, but when crystallization occurs at high temperature, it is BCC structure. Okay. So here in our case, we put beta titanium, right? So beta titanium is BCC. So we are dealing with the BCC crystal, and the lattice parameter and atomic mass is already given. Next, okay, answer is here. We have to find the first. We will find the atomic packing factor. Then we will go for the density. Okay. So we are using a simple cubic. So volume of the unit cell is A cubed, and this is the volume of the atom we already know, and the number of atoms in BCC, right, is 2. So when we solve this, we already know that the answer is 68%. That is the atomic packing factor. Then comes the density. So density is n into atomic number, atomic weight divided by volume of unit cell times the Avogadro number, right? So density is equal to the number of atoms, right? In BCC it is 2 atoms, and then we are using this value is already given. So just a sec. So guys, it will be really good if you would join on time for class, because it's kind of disturbing to move from screen to screen. Okay, fine. Um, so the number of atoms is 2 in BCC, and the atomic weight here of beta titanium is 55.847, which is already given. The volume of the unit cell also, the side is given. This is lattice parameter, right? So this is lattice parameter means A, and cubic means it is A cube, na? So that is also given here. The number of atoms is also given. So the density finally is 7876 kilograms per meter cube. So this is kind of a direct question only. Next, let's go for the Miller indices. So why should we know the importance? Like, why do we know? Why should we know the Miller indices? Because this is one good way to assess the material property, such as mechanical, optical, the reflective property. So everything we can find if we know the Miller indices. As I told you, even what type of material can also be found through Miller indices. It is one of the confirmatory techniques. Um, so let's go further. In the Miller indices, we have two things. Okay, that is the point coordinates, right? We can call them as intercepts. Okay, so either the intercepts can be at the corners, or it can be in the middle. In case the intercepts are at the corners, we can call them as 1. If it is not there, okay, if it's close to origin, then it is 0. Depends. We'll go deeper. And then if it's in the middle, it is half. Okay. So, oh God. Guys, am I audible? Hello guys, am I audible? Hello? Am I audible guys? Hello? Uh, guys, am I audible? Can anyone hear me? Oh God. Hello, am I audible to all? I'm sorry, guys. The problem is now we are having a very severe cyclone here. So I got power cut. So I think we will end class here itself today. So yeah, things not opening also. So thank you so much, guys. Thank you so much. We will end class today because of cyclone. Yeah, yeah. Yes, yes. Tell me, bro. Tell me. Yes. Gmail link, huh? Yeah, yeah. Sure, sure, sure. I'll do that. I'll do it. Just a sec. Yeah. Gmail link or Gmail ID? Gmail ID, right? Oh yeah, yeah. Sorry, sorry. That I'll try to share next week. It's not yet ready completely. So once that is done, I will send. But this is my email. If there is anything, you can contact me through this email. Anyone can contact me. Um, I'll send that. Yeah. Yeah, yeah. By for today, but next class I will have it ready. I'll give the notes. So next class will directly go for alloys because I think it's becoming too late. I thought I could finish, but the storm is too much. So they cut off the power supply, and net is also not working. So even my mobile data is very bad. That's why. So sorry, guys. Okay. Thank you so much. Thank you all once again for joining. Okay. Thank you, guys. Bye bye. See you next week. Yeah. Thank you. Thank you. Thank you. Thank you.